Welcome to the course on network theory. Today we are going to learn on the topic on Y parameters. So before going to discuss this topic, we shall discuss what we have done in the last lecture. So we have discussed the Z parameters. Z parameters. How did we write the equations? Initially, we have written the two equations, that is a1 v1 plus a2 v2 plus b1 i1 plus b2 i2 is equal to 0, and a3 v1 plus a4 v2 plus b3 i1 plus b4 i2 equal to 0. We have assumed here c1 and c2 as 0 because we assume that there is no dependent sources, right? And we have written this in compact form, that is a1 a2 a3 a4 into v1 v2 plus b1 b2 b3 b4 into i1 i2 equal to 0. So in compact form, this can be written as a v plus b I equal to 0. Then what we have done? We have taken this term into the right side. We are getting, so bi equal to minus ab. So if we are assuming that I are independent and we are dependent terms, then we can write b equal to minus a inverse bi. So if you assume this as z, this is z, then we can write this as b equal to z into I. So here A is a 2 cross 2 matrix and B is a 2 cross 2 matrix. A inverse also becomes a 2 cross 2. So my Z becomes a 2 cross 2. So if we expand it, then this will be V1, V2 equal to Z11, Z12, Z21 and Z22 into I1 and I2. If we try to expand this, we got the Z parameter equations, that is V1 equal to Z11 I1 plus Z12 I2 and V2 equal to Z21 I1 plus Z22 I2. So here you can see that we have assumed the port currents are independent and here port voltages are dependent. Here voltage are dependent on the port currents at input port and the output port. So think of the students where these always these port currents are independent. No, because there may be a case where the port currents cannot be independent and it's not applicable for a given network, right? So this should be chosen rightly. So what's the other way of choosing the port independent terms, that are voltages? So why we are trying to choose? Because for example, if you see this particular coefficient, that is Z is equal to A inverse B, right? So my Z parameter only exists when my A is invertible, nothing but A is non-singular matrix. So if you are able to get A as a singular, then your Z parameters will not exist, right? So in order to have a Z parameter, A should be invertible. So for example, let us consider a small circuit, a two-port network, right? So in which we are going to have a resistor R. This resistor is connected between the input port and the output port. Now, if we try to write these particular equations, we can see that my I1 is equal to minus I2, right? Because I1 is coming from left to right and I2 is coming from right to left. So I1 is equal to minus I2, which implies we can write I1 plus I2 equal to 0. What the other equation we can write? Here V1 plus V1 in terms of V2. So my V2 can be written as V1 minus, let us say current I1 is flowing through R, so we are going to have a voltage drop. So V1 minus I1 into R, right? So if you try to write this equation here, V1 minus V2 minus I1R equal to 0. So if you try to write these two equations in generalized way in this particular format, so how can we write? So it is 0 into V1 plus 0 into V2 plus 1 into I1 plus 1 into I2 is equal to 0. Now we have 1 V1 minus 1 V2 minus R I1 plus 0 into I2. So my A matrix is, it is 0 0 1 minus 1, and my B matrix is 1 1 minus R 0. So you can see here that my A matrix is not invertible, as A is a singular matrix. Therefore we need to go for other type of parameters. Here we are going for the Y parameters, that is by considering V as voltage as a independent, whereas current port currents are dependent. Let's recapitulate what we have discussed till now. So we have seen that in Z parameters where current are independently controlled and voltage responds to these particular port currents. However, we have seen that Z parameters cannot be computed for all the ports. That is, Z parameter can only be applicable where my A matrix is invertible. Right? So we are making this assumption that A is invertible, then only we are able to compute our Z parameters. If this assumption fails, then we are not going to have a Z parameters. So what is the other solution? We are assuming that voltage are independently controlled and the currents are response to the changes of these particular voltages, and this property or this parameter we call it as a pi parameters, or sometimes called as admittance, because it's a ratio of the current to the voltage, and these parameters or admittance parameters are written in this particular way. So how did we got this matrix form or this in scalar form? See, rather than, for example, if you try to see here, rather than inverting A here, what we have done, we are trying to invert the B. So we have Bi equal to minus A into B. Try to invert B. So we are going to have I equal to minus B inverse A into B. So if we assume this as the Y, as Y is the ratio, nothing but the ratio of current to the voltage, which we call it our admittance matrix. So if this B is a 2 cross 2 matrix and A is also a 2 cross 2, then we are going to say that this Y is also a 2 cross 2. So if you try to expand this one, where we have assumed that I equal to I1 and I2, which is equal to Y11, Y12, Y21 and Y22 into V1 and V2. So if you see here, if you try to expand further, we can write I1 is equal to Y11 V1 plus Y12 V2 and I2 equal to Y21 V1 plus Y22 V2. So here we are assumed that our port voltages are independently controlled and here currents are response to this change in voltages, port voltages. So these are called Y parameter equation, and this is in matrix form and this is in the scalar form. So next question comes in our mind that how do we determine these Y parameters, Y11, Y12, Y21 and Y22 by short circuiting the input and output ports. So if we try to short circuit the output port, so if we are trying to make this particular term equal to 0, right? How? We are trying to make this V2 equal to 0. We cannot make Y12 is equal to 0. This is the one which we are going to compute it. So if we are trying to short circuit the output port, then this particular term and this particular term will be equal to 0, right? So once we have eliminated this particular term, we can compute y11, y11 and y21. So my y11 becomes I1 by V1 and y21 becomes I2 by V1. Okay. This has happened when my V2 is equal to 0. We are trying to short circuit it. And similarly, how do we compute this y12 and y22? We can compute this one y12 and y22 by eliminating this particular portion, that is y11 and v1 equal to 0, and we can compute y22 if we are able to make this y21 and v1 equal to 0. How do we make? By short circuiting the input port. So if you are able to short circuit this input port, so we are trying to make these terms as 0. As a result, we will be able to compute my y12 and y22. So my y12 can be given as I1 by V2 when my I1 is V1 equal to 0. Similarly, this is y22 is equal to I2 by V2 when my V1 is equal to 0. So if you observe, we are able to compute y11, y12, y21 and y22 if we are trying to short circuit the input and output ports. So the other name for these y parameters is the short circuit parameters. So this y parameters is also known as the short circuit parameters. Let us see what are the names. How do we define these parameters? See, here y11 is equal to I1 by V1 when V2 is equal to 0. So we are trying to short circuit. We can name it as short circuit, and we are trying to excite at the first port, and we are trying to take the response of the first port. It's a driving point, and we are exiting at first port and getting the response of the same first port. So it's an input port. So input, and the ratio of I by V is called as admittance. So y11 is the short circuit driving point input impedance seen looking into port 1 when port 2 is shorted. And how can we name y21? Again, is the V2 equal to 0. It's a short circuit. And we are exiting at first port, and we are trying to take the response at the second port. It's a forward transfer, and the ratio of I by V is the admittance. So we can name it as short circuit forward transfer admittance. So it is the ratio of the current induced at the port 2 to the voltage applied at the port 1 with port 2 as shorted. Similarly, when we are trying to make V1 equal to 0, nothing but we are trying to short circuit it. So short circuit, and we are trying to excite at second port, and we are trying to get the response at the first port, right? So it's a reverse. So reverse transfer admittance. It's a ratio of I by V. So it's a reverse admittance. Okay, it's a short circuit reverse transfer admittance. Finally, the last one here, it's a y22 is known as a short circuit. It's exciting at second port and getting the input out. Response at the second port itself. It's a driving point, output admittance. So y22 is otherwise called as short circuit driving point output admittance. We are trying to see the looking at the port 2 when we are trying to short at the port 1. So actually this should be the output. It's an output. Now let us take a small example and derive this particular y parameters. So let us take a small circuit. Let us assume we have a resistance here and we have another resistance, and let us say we have another resistance here. So this is V1 plus minus, and this is I1, and this is I1. Let us say this is output port V2, and the current at the output port be I2, and this is the I2. Let us say this is resistance R1, R2, and R3. Now let us apply our nodal analysis. So in order to apply our nodal analysis, the first step in nodal analysis is to identify the nodal voltages. So how many nodal voltages we have? We are having 3 nodes, that is the first one, second one, and third one. So let us assume that this first node and second node are non-reference node, and the third node is a reference node. So let us redraw the circuit over here. And how this circuit is looking? It is looking like a pi network. So this is V1 and this will be V1 because there is no voltage drop across this particular 2 nodes, and this is V2 and the current injected here is I2, and the voltage at this particular point also will be V2, and the outgoing current here is I2, and the outgoing current at this particular terminal is I1, and the values is R1, R2 and R3. So if we try to apply our nodal equations here at node 1 and node 2, what we are going to get is that I1 is the incoming current, and let us compute the outgoing currents. So how do you compute? We are having 2 branches over here. Let us say the current flowing through this particular branch is V1 minus V2 by R2. So we are trying to assume that V1 is greater than V2. As a result, current is an outgoing current, and as V1 is greater than 0 volts, here as we assume this is a reference node, so it is V1 minus 0 by R1. So if we try to rearrange this particular equation, we get I1 equal to 1 by R1 plus 1 by R2 into V1 minus V2 by R2. Similarly, if we try to apply nodal equation at node 2, we can observe that the incoming current is I2 and the outgoing current is V2 minus V1 by R2 plus V2 by R3. So here we assume that when we are trying to write the nodal equation at the node 2, we assume that V2 is greater than V1. So as a result, the current is an outgoing current. So it is V2 minus V1 by R2. As V2 is greater than 0, it is V2 minus 0 by R3. Okay. So if you try to rearrange this equation, I2 is equal to minus 1 by R2 into V1 plus 1 by R2 plus 1 by R3 into V2. So if you try to compare with our standard equations, that is I1 equal to Y11 V1 plus Y12 V2 and I2 equal to Y21 V1 plus Y22 V2, we can see that my Y11 is equal to 1 by R1 plus 1 by R2 and Y12 is equal to 1 minus 1 by R2 and Y21 is also equal to minus 1 by R2, and the last one is Y22 equal to 1 by R2 plus 1 by R3. So if we assume that R2 equal to R1 equal to R3, then we can write here 1 by R3 plus 1 by R2 and 1 by R2 plus 1 by R3, right? So by seeing this, what you understand here is that my y12 is equal to y21. So this happened only because our circuit is having only a passive elements. There is no dependent elements, right? So we can, whenever my y12 is equal to y21, we are going to say that my circuit is a reciprocal circuit. And when we made R1 equal to R3, then my y11 became equal to y22. It means that the circuit behaves similarly whether we apply seen from the port 1 and port 2. So we are going to say that port 1 and port 2 or input and output behave in the similar way, and we are going to say that the circuit is a symmetrical circuit. So whenever we are going to say y12 equal to y21 or my I1 dash equal to I2 dash, then we are going to say my circuit is a reciprocal. So we have considered any network here, say network N, and we are trying to short this particular output port. That is, we are trying to make V2 equal to 0 and exciting at the input port. That is, my source voltage is equal to V1. We are going to have two currents, that is I1 and I2. And I2 is nothing but minus I2 dash. Now what we are trying to do, we are trying to exchange the response and the excitation branches. So here we are trying to excite it in branch 2 or at the output port, and we are trying to take the response at the input port. So here my I1 is equal to minus I1 dash. So whenever this my I2 dash is equal to I1 dash, we are going to say that the ratio of response to the excitation is same. As a result, we can say that my circuit is a reciprocal circuit, as this happens only when my y12 is equal to y21. Similarly, a two-port network is also said to be symmetrical if its ports can be interchanged without changing the port voltages and current. That is, the circuit is said to be symmetric if the ratio of I1 by V1 is equal to I2 by V2, or whenever we say my y11 is equal to the y22. Now let us draw the equivalent circuit for y parameters. So before going to draw the equivalent circuit, we shall recapitulate the equations, y parameter equations. That is, I1 is equal to y11 V1 plus y12 V2, and we have I2 equal to y21 V1 plus y22 V2. So here voltages are port voltages which are independent, controlled independently, and these are dependent. So if you observe these two equations here, the total current is getting divided here. So this will be my current, and this will be my amperes part, right? So here the current is getting divided. So we should connect these two in parallelly. Okay. So let us say we are having a two parallel thing, or let us draw. Okay. Here we are having a two-port network. Out of which we are trying to drag the four terminals. So we are exciting the ports with the voltage sources. So your V1. So we are having V2 here. So this will be my plus and this will be my minus, and let us say this is plus and this is minus. As it's a closed circuit, we are going to have current I1 injected over here, and there is a flow of current I1 over here. Similarly, I2 is going inside here, and let us say the I2 is coming out of here. Say here this is the I1 current. So this I1 current is getting into divided into two parts. So this I1 should have two branches. Say we are having one branch over here, and let us say we are having another branch over here. So this V1 and these two branches are connected in parallel. So whenever we have any elements connected in parallel, then we are going to say those elements are having same voltages, potential difference across those two terminals, right? So as if you try to see, we are having V1 and we are having V1. So we should have an element here, say that is Y11. So the current flowing through this is Y11 into V1. Similarly, we need to take the current flowing through this particular branch, but it is a function of V2. So what should we take? We need to take a dependent current source. What the direction? The current is coming from top to bottom. And what's the value of it? The current, it is Y12 V2. So we have taken a voltage dependent current source. Similarly, if you try to take from the second port, so the current is getting divided among two parts. So it means that we are going to have two branches connected in parallel in this particular way. So if you see here, I have this I2 and we are having Y2 to V2. It is nothing but as these three branches are connected in parallel, so we are going to have an element here which is Y22, which is connected in parallel with V2. So the voltage across this will be V2. So the current flowing through will be Y22 into V2. And what will be the here? We need to have a current here, but if you see, this is a function of V1, voltage at the first port, injected at first port. So we need to take a dependent source, and let us say we are going to have a current going from top to bottom. As the current comes over here, it gets divided among two branches, so current will be from top to bottom. And what will the value of it? It is Y21 V1. And whenever it comes here, my I1 will be equal to Y11 V1 plus Y12 V2, and my I2 will be equal to Y22 V2 plus Y21 V1. So this is my equivalent circuit of Y parameters. Now let us compare our Y parameters with the Z parameters. Let us draw a table. So let us write Z parameters here, and this is Y parameters. These Z parameters, what the parameters we have? Z11, Z12, Z21 and Z22. These parameters are able to find by opening the circuit. So we call these Z parameters as open circuit parameters. Similarly, here what are the Y parameters we have? Y11, Y12, Y21 and Y22. These parameters are computed by short circuiting the input and output port. So these Y parameters is otherwise called as short circuit parameters. So, and the second difference is that when we are trying to compute these parameters, we try to make use of mesh analysis. So by applying mesh analysis, we'll be trying to get directly the Z parameter equations. That is, we can compute Z11, Z12, Z21 and Z22 directly. And when coming to the Y parameters, we are going to apply nodal analysis. So you can see, for example, how did we do that? So we are having the Y parameter. See, this equation and this equation are directly in the form of our conventional Y parameter equations. So our y parameters are easily computable by applying the nodal analysis. What is the applications part? As this is a mesh analysis, so we are talking about the voltages. So we try to apply our Z parameters whenever the two subnetworks are connected in series. And these 5 parameters, we are talking about the nodal analysis, that is current, right? So whenever these two subnetworks are connected in parallel. So these are the some of the different comparison between our Z parameters and Y parameters. And if you are talking about this symmetrical and reciprocal conditions, my Z parameters are reciprocal if my Z12 is equal to Z21. We are going to say the circuit is reciprocal. And for Y parameters, if my Y12 is equal to Y21, we are going to say the circuit is reciprocal. Similarly, when we talk about the symmetrical condition, when the circuit is said to be symmetrical, when we are trying to apply our Z parameters, whenever my Z11 is equal to Z22, we are going to say the circuit is symmetrical. Similarly, for Y parameters, whenever my Y11 is equal to Y22, we are going to say symmetrical. And do remember that my Z parameters exist if my A is invertible. And my Y parameters exist if my B matrix is invertible. Okay, if you see here our derivation, we have assumed that our B is an invertible matrix. As a result, we are going to get the Y parameters. So our assumption for Y parameters is that B is invertible, and similarly for Z is A is invertible. So let us stop here with the comparison of Z parameters and Y parameters. In the next lecture, we shall see the real world applications of our Y parameters, and we shall solve some numerical problems on it. Thank you.